Last time we looked at the derivative of an exponential function, but not just any exponential function, the exponential function with the simplest, easiest derivative to do. Today, we'll look at an introduction to logs and derivatives with logs. To do that, we're going to start with some review from MHF4U. How do we solve some different exponential and logarithmic equations? If you have an exponential equation, like in part A, and you can't write the same bases, so in this example, if this was equal to 8, it would be easy because 2 cubed is 8. So we know the value of x would be 3. But we don't have that in this case. We don't know. So one of the techniques you used was to take the log of both sides. And the reason we did that was because one of the properties of logs or the log laws is that the exponent can come out to the front and that changes a logarithmic equation to a linear equation. So let's do that. Let's take the log of both sides. So I will take the log 2 to the power of x is equal to the log of 5. Now we can bring that power down to the front and we get x log 2 is equal to log 5. Now it's a little bit easier for us to solve for x. We can divide both sides by log 2. That leaves us with x is equal to log of 5 over log 2. And then using that change of bases identity that you may have seen in functions, or hopefully you have, we could rewrite this as log 5 to base 2. So this could be log 5 to the base of 2. And this just means that it's base 2 instead of 10, base 10 for both of those logs. This property always works. So you could do that, or on your calculator, you could plug in log 5 divided by log 2 and get a decimal that is approximately equal to log 5 base 2, which is 2.32. So 2 is 2 to the approximated 2.32 would give you a value of 5. Now let's look at this next one. If you wanted to solve a logarithmic equation, one of the techniques that you can use is to write it exponentially. So in this case, where there is no base, remember, it's implied that this is base 10. So to write this exponentially, we could simply say that this is x is equal to 10 to the power of 2. If you forget how to change from a logarithmic equation to an exponential equation, the big idea really is that the base, so the base that's here, in this case 10, becomes the base. So the base of the log is the same as the base of the exponent. If this is 10, then this becomes 10. If it's a base 2, then the base of our exponent is 2. And then the log becomes the exponent. So this means that x equals 10 to the power of 2, or x is equal to 100. So that's another rule. I'm trying to jog your memory so that you can remember. Now, we could approach problem C the same way we did the first problem. We could take the log of both sides. We could move the exponent in front. So let's go ahead and take a look at that. So we're going to take the log of both sides. So we have log of e to the x equals log 4. Now we want to move that power down. That's the nice thing with doing it this way. So x log e is equal to log 4. Now we divide out both sides by log e, and we end up with log 4 over log e. So we can rewrite this in this case as x is not equal to 10g. Got ahead of myself there. Not equal to 10g at all. So x is equal to the log 4 base e. So log 4 base e. We know that base 10 is on our calculator, but base 2 isn't. But base E should be there on your scientific calculators. You might not have used it before, but it is there. And that is the log that we're going to look at today, the log of base E. Another topic from MHF4U and MCR3U, this idea of graphing exponential functions from 3U and then logarithmic equations from 4U, is what we're going to look at right now. So all of these equations that you can see, all these graphs, all of the equations in blue are just y equals b to the x. We know that it's just b to the x, that there's no number in front of it, because the y-intercept is 1 and the asymptote runs through 0. So we end up with an asymptote that runs through 0. So in this first case, we know that the base must be 2, since 2 to the power of 1 is equal to 2. And if we just look at the graph, we actually can see it. So we look at the graph, we go over 1, and our next y value is 2. So this equation for this one then must be y equals 2 to the power of x. That means that the red equation, since it's reflected over this x equals y, must be the inverse. So the one in red then has to be, since it's the inverse, the one in red has to be x equals 2 raised to the power of y. So if we wanted to, instead of writing it as x equals 2 to the y, remember the inverse just means we switch the x's and the y's, we could rewrite this as the natural logarithmic equation. We could rewrite this as y equals log x to the base of 2. So y equals log x to the base of 2. In the next example, is basically the same. The horizontal asymptote is still at 0. The intercept is at 1. So if we zoom in on this, we can see that the intercept is actually at 1. So we know that this has to be a y equals b to the x. The next point that we're looking at here, the next point that we want to look at is if we go over 1 and go up to the next y value, our next y value is 10. So since that next point is 10, this means that this must be equal to y equals 10 to the power of x. So y equals 10 to the power of x. Again, the red one is the inverse because it's the reflection over the line y equals x. So this must mean that for this bottom one then, that x is equal to 10 to the power of y, or we can rewrite this as y equals the log x. And remember, if there's no base given, we assume that it's base 10. So y equals log x is the inverse of x equals 10 to the power of x. Now let's look at this last one. Now, if you're not sure what the base is for this next one because it doesn't look very clear, think about approximately what it might be. So if I go over 1 and I'm looking to come up to my next y value, I can see that it's somewhere between 2 and 3, but a little bit closer to 3 than 2. And this, in fact, is y equals e to the power of x. So this is about 2.718. So remember, e was about 2.718. And the red one is the inverse of y equals e to the x, which means it's going to be y equals the log of x to the base e. And this one, again, is on your calculator. It just doesn't look like this. And this is called the natural logarithmic function. It's called the natural logarithm, and we're going to take some time to talk about that here in a second. I've gone ahead and included a little bit of extra information just about some of the properties of y equals e to the x, just as a refresher from the last lesson, the video that I posted. So take some time and pause the video or go back and look at this in the notes for today's lesson, just to refresh your memory about this. Basically, all the properties of exponential functions and logarithmic functions are familiar. You are familiar with also apply to the exponential function. So everything that you've done for logarithmic applies to the exponential. And that's really what we're going to take a look at today. Okay, back to this page. So, like I say, we're familiar with this. It's called the natural logarithm. So, just like e is the nicest base for the derivative of exponential functions, base e is the nicest base when we have to take derivatives of logarithmic functions. In fact, it's used so often, it's given a slightly different notation. So, the notation that we have is this here, and it's pronounced ln x, and it stands for the logarithmus naturalis. So instead of writing log base e, you're now just going to write ln, and this is the button that's on your calculator. So it is the inverse of y equals e to the power of x. It's the graph we just looked at, and that means exponentially that we can write it y equals ln x as x equals e to the power of y. So we can rewrite it that way. Just like with other logs, we have all these different properties. So let's think about these. So the first one, we have ln of e equals 1, essentially e to the power of 1, since e to the base equals e. Now, e to the 0 equals 1, so ln 1 must then equal 0. So ln 1 must equal 0. E to the x equals e to the x. The idea here is that they cancel each other out. They are inverse, so ln of e to the x just equals x. And similarly, e to the ln x equals x. E to the ln x equals x. Sorry, I'm going to say that one again. So e to the ln x equals x. So really just, e to the ln x equals x. I don't know why I keep saying it over and over again. I guess I feel that it's important. So in general, if we take a look at what's happening here, we can see that we have the derivative of whatever is on the inside of the function, or that piece that we're taking the ln of, all over whatever the original function is. So when we had the derivative of y equals ln x, it became 1 over x. Derivative of x is 1. Derivative of ln is 1 over x. So we're going to hold on to that, and we're going to look at some examples. So in example A, we have two functions that are multiplied together with x's. They both have x's. So we can use the product rule. So we know that the product rule tells us we take the first times the derivative of the second. So my derivative here would be y prime is equal to my first, which is x, times the derivative of my second. The derivative of ln x is just 1 over x, plus the derivative of the first times the second. The derivative of x is just 1, and the derivative and times ln x. We can simplify this a little bit. These x's cancel each other out. So the derivative of y equals x ln x will be equal to, the derivative is equal to 1 plus ln x. There's our derivative. This is what we're left with. For this next one, we have a function inside a function. So we're going to use the chain rule. And really what we're going to do is we're going to lean into this idea that we had here for our general equation, that it's the derivative of the inside, so derivative of the inside, which in this case was x, all over just that function. So the derivative of the inside times the function, over the function. So we have ln of 2x plus 1. We're going to take that 2x plus 1 as being the inside, and we're going to take ln as being the outside. Well, we know that the derivative of ln is just 1 over x. And so if we have, it would be 1 over whatever is on the inside. So it would be 1 over the inside, 2x plus 1. And that's going to be times the derivative of what's on the inside. And the derivative of 2x plus 1 is just 2. We can simplify this to be 2 over 2x plus 1. So the derivative of y equals ln 2x plus 1 is simply 2 over 2x plus 1. The easiest way to remember this is that for the ln of a function, the derivative of the inside goes on top and the function goes on the bottom. So let's take a look at this next one, and this next one is exactly the same as what we just did. So we know that it's going to be that the derivative of the inside goes on top and the function goes on the bottom. So our derivative of the inside, the derivative of x squared plus 2x minus 5, will be 2x plus 2 all over the original function. So our derivative of y equals ln x squared plus 2x minus 5 will be 2x plus 2 all over x squared plus 2x minus 5. The derivative goes on top, the function goes on the bottom. Now, this last one here is y equals ln x plus 1 all over x squared minus 3. Logs have some properties that make some of the derivatives a little easier to work with. So this looks like it would be the quotient rule question, but it doesn't have to be if we use our log laws. So remember, subtracting two logs is the same as dividing. So we could rewrite this as y equals ln of x plus 1 minus ln of x squared minus 3. Now we have two easy derivatives because we're going to treat this the same as we treated this one and this one. We're going to do exactly the same thing. Okay, so we're going to take the derivative. So the derivative of ln x plus 1, remember the derivative goes on the top. So the derivative of the inside goes on the top. X plus 1, the derivative of that is just 1 all over the original function, x plus 1, minus, same thing, derivative of the inside. So x squared minus 3, the derivative of that is just 2x all over the original x squared minus 3. So that's the derivative. So hopefully now you have a little bit better understanding of how to take the derivative of the natural logarithm, or ln e. And there are some homework questions to complete. From our textbook, it's page 265, 8 to 10. And I have included another handout on the VLE that has some additional questions. Because of that, there will not be an exit ticket for today's lesson. If you have any questions, feel free to send me an email.